Good afternoon, everyone. So, before starting today's classes, I am introduce myself. So, I am Povir Maiti. I am taking that course of polymer concept, properties, uses, and sustainability. The course instructor was Professor Abhijit P. Deshpande. So, last classes we have solved some problem regarding the condensation polymerization. So, today's classes we are going to solve something problem about that copolymers and liquid crystalline polymer. So what are the polymers? So if you classify the polymer, there will be two types like that, homopolymer and copolymer. So why we need this copolymer? Because if we are going to for the homopolymers, and we need to that our polymer should be applicable in various, like it's also applicable in high temperature region and also applicable in low temperature region. So for only one polymer that cannot be possible. So if we are making a copolymer, so that we can arrange the monomer units such a way that our polymer can be applicable for both of the applications. So for this reason, we are supposed to go on to from the homopolymer to copolymer. So there are various type of copolymers are present, like random copolymers. So when we are talking about that random copolymers, so like a homopolymer would be like if your monomer is A, and if you only in your polymer system only A are present, so this will be our homopolymer, like this. So this will be our homopolymer. And if in your polymer system there will be two monomer unit present like A and B, and how they arrange of A and B, that depends on that what type of copolymer it is. If the A and B is arranged like a randomly, like A, like this way, so this are type of the random copolymer. So there will be no arrange between the A and B. It will be randomly orientated in the polymer chain A and B monomer unit. And if you are going for the alternating copolymer, so alternating means that we add to the alternate position there will be A and B. So always they are repeatable A B like this. And when we go for the block copolymer, so like a block, so there will be different block of A, then block of B. If like this block are present in our copolymer system, then we call it as block copolymer. And graft copolymer is like this. When your main chain is a one polymer's main chain, like this way, and your pendant group, like in your side chain, there will be another polymer system, like this. So this will be our graft copolymers. So how we can control that our polymer should be random copolymer, alternating block copolymer or graft copolymer. So that we can do by that reactivity of these two monomers, like a monomer chains, and it will be take only A. So reactivity of that rate constant for getting A will be this, and if this will be A taking as one monomer from the B, so rate constant for that copolymer, that will be AB. So rate constant of the KAB. So when the KAB is higher, that means the taking to probability of A to taking B, that will be increase. So that the reactivity ratio of A, that is the rate of that homopolymer, like AAA divided by rate of taking as B, AB, and reactivity ratio of B, that is the getting homopolymer of B and getting that B alternating B polymer. So how we can get that which one will be alternating, and which one will we get the block copolymer, and which one will be gradient, and which one will be random copolymer. So that we can consider by a simple technique. So if you show that in this that first one, the reactivity of Ka, that means that our monomer chain will be can consume this A. So if A consume this A, so that they are going to be a homopolymer. But if A taking a B, so then that will be AB type of polymers, that is AB that will be repeatable. So if AB is repeatable, that is our polymers is going to a alternating one, that is that type. So when that will be increased, so if a such position where the Ka value is very minimum and Kab value is maximum, so it will be minimum. So when the chance of the alternating, so alternating chance will be then when our Ka chance will be very minimum and Kab chance will be very maximum. So then these cases we are getting the alternating one. So for the alternating copolymers, we have remember that should be our that A taking to B will be maximum. When that will be cases, so our RA will be such like that when there will be KAB is very maximum. So if something is minimum and divided by maximum, so what do we get? 1 divided by infinity is almost equal to 0. So the probability of alternating copolymer will be when there will be Ra and Rb is equal to 0. And when there will be random copolymer means so there will be no probability of taking as A and no probability of taking as B. So for that the cases, if there will be there will be no probability of taking A and B, and both are probable, like this monomer can consume this A, this monomer consume this B, are they equal probable, then they can, that one time they can take 2A, one time they can take 1B, or one time they can take 2B 1A, like this. So there will be no arrange in the polymer chain. So then then we are going to get that random copolymer. So for that random copolymer, so our reactivity ratio of between these two will be same, that will be both homo and both that random that alternating one are equal probable. So when we are getting block copolymer, so for that getting block copolymer, so our Ra and Rb should be very greater than 1, that is the chance of getting homopolymer will be much greater than that the chance of getting that 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 is the AB type. So chance of getting AA type is very much greater than, or chance of getting BB type is very greater than. So then can we then we can get that block copolymer. And when we get that gradient copolymer, if a such a system like that, when there will be probability of that getting A is not very greater than 1, but it will be greater than 1 like that. So it will be after sometimes after 10 units of A taking, so then that will be B are taking, like that the gradient wise it will be increases or gradient wise it will be decreases, then 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 we can get the gradient copolymer. So from that reactivity ratio of our polymers, we can get that both alternating random block or gradient copolymer as we want. So we have to just to keep the reactivity ratio of these two monomer like such a way that what we want to get we can get from this. So for this so how the reactivity ratio of different of the various polymers for that random copolymer, that is the Ra and Rb equal to 1. So in these cases the alternating for the alternating cases copolymers, we are getting that Ra Rb is almost equal to 0. So this so the reactivity of these monomers Ra and Rb are generally 1. So then we can get that the reactivity ratio is towards each other. So we are getting random copolymer. And when we are getting alternating copolymers, so earlier step, when there will be probability of AB, that is the KAB is very much, or KBA is very much greater than KAA or KBB. So then we are getting alternating copolymers. And when Ra is very greater than Rb, or like the reactivity ratio R equal to very greater than 1, in a, we are getting the block copolymer. So block copolymer, one of the reactivity ratio is either Ra or Rb is significantly greater than others. This indicates the monomer has a much higher reactivity towards the growing polymer chain than the other monomer. So now we are going to some another example like the liquid crystalline polymer. So for the liquid crystalline polymers, so what are called the liquid crystalline polymers? So liquid crystalline polymer are a class of materials that exhibit both the properties of conventional polymer and ordered and isotropic behavior of the liquid crystal. So we know that liquid crystal there will be behavior like ordered or anisotropic behavior, and conventional polymers have the behavior like the material properties wise applications. So if a polymer like both the behavior present in the polymer system, like it can behave as a polymer, also it can behave as a liquid, so it will then we call as a liquid crystal polymer. They have the unique molecular structures and properties that make them a valuable in various high performance applications. So the some key characteristic and application of liquid crystal polymers are I will give. So the liquid crystal polymer, if you are going for the crystal, so crystal are arranging in the order. If you increase the temperature, so the our order crystal will be there will be no order. So but there will be chance, there will be both the probability of properties like a behavior of liquid and behavior of crystal, both are possible. And when increase more temperature, then we are getting the liquid type of behavior. So liquid crystal properties is the middle of the both between the crystal and liquid properties. So something a example of liquid crystalline polymer, like a liquid crystalline polymer such a way that there will be some aromatic groups which are mesogen and which are linked with some flexible linker. So then this give a liquid crystalline polymer. For liquid crystalline polymer, there will be various phase like symmetric C phase, symmetric S phase, pneumatic phase, or isotropic phase, and this is the crystalline phase. So liquid crystalline are the various phase, and in next class onwards we want to go that how we can identify that these are the liquid crystal polymer, what are the characterization technique of liquid crystal polymers. We're going to solve in the next classes onwards. So what are the behavior of this type of liquid crystal polymer? So as I told, like that the liquid crystal polymers are that type of polymers where we are getting both the behavior of solid, that is the polymer behavior, and also we get the behavior of the liquid type of behavior. So like the behavior like the anisotropic behavior. Anisotropic behavior is such like that. Anisotropy meaning that the physical properties such as material, thermal, and optical and directionally dependent, and this anisotropy is due to the alignment of the polymer chains in a specific direction. So that means our polymer should be in a specific direction or specific orientation. The polymers behave that such a way that its properties going to change like mechanical property or thermal property. So if the arrange of this crystal in the system will give that our mechanical, thermal and optical property are different. An ordered molecular structure, the LCPs have the well-ordered molecular structure obtained with rod-like or plate-like segment in the polymer chain. This ordered structure contributes to their unique properties, high thermal stability. Like the liquid crystal polymers have contained some aromatic groups in the polymer chains, which have that higher thermal stability as compared to the liquid, and maybe lower thermal stability compared to that or conventional polymers, but it's have the high thermal stability than our conventional liquid. LCB typically exhibits high thermal stability and can withstand high temperature without significant degradation. This makes them a suitable application involving exposure to heat. High strength and stiffness. Liquid crystalline polymers have mechanical properties including high strength and stiffness, which make them an ideal structure for load-bearing applications. Low CTE, that is the CTE means the coefficient of thermal expansion. LCBs have the low CTE, meaning they expand and contract less with change in temperature compared to the many other polymers, with property in beneficial in the application where the dimensional stability is critical. So where we are going, dimensional stability is very much important. So then there will be the low CT's properties will be applicable. So the liquid crystal polymer are like the anisotropic behavior. So that is that directionally that the properties of this polymer are going to change. So they have the ordered molecular structure, they have the higher thermal stability, they have the higher strength and stiffness. Also, they have that low coefficient of thermal expansion. That is that within changing temperature they are contract and expand less as compared to conventional polymers. So this suitable characteristic of these liquid crystal polymers are very much effective in various applications like electronics. LCPs are the most electronic device and circular security and circuity due to their excellent electrical insulating properties, high temperature resistance, low dielectric constant. They are used in the connectors, flexible circuit boards, and other electronics components. Like that, when you are going to that polymers which are not flexible, but the liquid crystalline polymers which are that there will be some flexible chain in between these polymers, so they also can used as a flexible circuit board. So this advantage make them to application in the electronics. Also in automotive, where the high load bearing capacity we needed, so LCBs can applied in this industry, automotive industry also, especially under the food components, because they are the ability of withstand high temperature, resist chemicals and automotive fluids. So automotive industry we need to withstand the high temperature, high load bearing capacity and resist the chemical also. So the liquid crystalline polymer also used in this process. Also liquid crystalline polymer used application in the aerospace because of its lightweight and high strength capacity. In medical devices also liquid crystalline polymer are used in the equipment due to their biocompatibility, resistance to the sterilization process, dimensional stability. Example like catheter, surgical instrument and implants, etc. So in these classes we have talked about the liquid crystal polymer, how they are behave, and what are the characteristic properties of the liquid crystal polymer. In next class onwards we're going to discuss about the liquid crystal polymers. What are the main characteristic tools to identify these liquid crystalline polymers, and what are the instrument we can use for this liquid crystalline polymer. Now we're going to solve some problem like mathematical. So So now we are going to find out a relation between that degree of polymerization and average functionality and extent of reactions. Average functionality is needed because when we are going to two monomers functional condensation polymers, two functional group we are giving. So, and if there will be some excess and there will be more than two functionalities present in the polymer system, so we need to calculate the average functionality always. So if we are going to average functionality, how this molecular extent of reactions will be related with our average functionality. So let's consider like N0 is the total number of molecules or monomers of all type present initially, and in the total number of molecules when the reaction has been proceeded. So N0 minus N will be the number of linkages formed at the extent of reaction. So this follows the fact that every time a new linkage is formed and reaction mixture will contain one less molecule. So every time two functional group are linked, so we are getting one molecule. So we are loses every time two functional group are linked. So we are lose one molecules from the reactant side and one molecules we are getting from the product side. So two functional groups react to form one linkages. So moles of functional group lost in the forming N0 minus N molecule, that is the 2 into N0 minus N. Thus the extent of reactions, that is the number of functional groups we have used. So total number of functional group we have used, that is the 2 into N0 minus N, and the total numbers of functional group present initially, that is the N0 into F average. So from there we can calculate the value of N, and we know the degree of polymerization Xn bar equal to N0 by N. So if you put this equation N0 by 2 and value of N here, we can get the relation between the degree of polymerization and F average. So now we can calculate some problems. So how that is we have to calculate the functionality of this glycerol and phthalic acid. So if you're going to solve this problem, so how we can solve? So we have to calculate the F average of these two molecules. So F average of this, the mathematical equation for the F average equal to summation of N into F average divided by summation of number of molecules. So average functionality of number of moles into F average are divided by total numbers of functionality present in our system. So from here we have the 2 moles of glycerols, and glycerol have 3 functionality. So R will be 2 into and divided by N, total number of molecules. So 2 into 3 plus, for this case is phthalic acid, 3 into the functionality is 2 divided by total number of molecules, that is the 2 plus 3, 2 moles and 3 mole. So that will be 12 by 5 that is 2.4. So if you're going to solve some mathematical problem and from that F average to that, how we can calculate the degree of polymers. So first we have to calculate that F average of this molecule, then we have to can calculate that. If we know that extent of reaction, we can calculate the degree of polymerization by this equation, because our degree of polymerization is related to our F average and extent of reactions. So for this, I am going to solve some problem like that. For some application, nylon 6 is desirable to have. We want to get a molecular weight 20,000. For making these polymers by polycondensation of the hexamethylene diamines and adipic acid, how much acetic acid per moles of adipic acid should be added to get that Mn? So we know that relation between that Xn bar and this 2 by P into 2 by 2 minus PAF average. So from there we have to calculate the degree of polymerization. So for this degree of polymerization, so for we know that linol 6s have the total repeating unit 2 to 6, but there will be two functional groups, so we have to divide it by 2. So from here we are going to calculate, that is the 113, the repeating unit. So the xn bar equal to will be our molecular weight, that is the 20,000 divided by 113. So from here we can calculate the xn bar. Now the what, so we are getting xn bar, it is almost equal to 177. So from here we can calculate the F average, and our F average will be 1.9887. So let's assume that we have add the monofunctional impurity, how much acetic acid. So acetic acid act as a monofunctional impurity, and next class onwards also I'll tell about that how the monofunctional impurity are going to control our molecular weights, how this monofunctional impurity will be going to control our molecular weight, so that we can teach in next classes onwards. So if we, this are acetic acid are the monofunctional impurity, so from here we get the F average equal to 1.9887. So now we have to calculate that the F average. So F average means the total number of functional groups divided by total moles present, that is the total moles present of hexamethyl diamine, 1 mole, and we are going to give that let's assume that x mole of acetic acid we are going to give. So the total moles we are getting 2 plus x, and the total number of equivalents, that is the limiting group. So we are getting that functionality for the above cases is 2. So 2 into 1 plus 2 into 1. So the above will be total number of functional group will be 4 divided by 2 plus x. So if you solve this one, so from here we can get the value of x. So if you are getting the value of x, so that is the how much of acetic acid we can add into that system, that we can get that exact molecular weight of 20,000. So if we're going to the recap of today's classes, so today's class we have to learn. So you have learned about that, you know about the polymers. So polymers are making, polymers are those where that our monomer units are connected to each other. So the if we classify our polymers as a behavior of the how the monomer chains are present in the polymer chain. So there will be two types like homopolymers when there will be one monomer unit present, and copolymer when there will be multiple monomer unit present. So if the copolymers, there will be various type of copolymer like random copolymer, alternating copolymer, block copolymer, graft copolymers, and all the copolymers are depends on the how the arrangement of the two monomer units present in the polymer chain. For the random cases, the monomer unit of A and monomer unit of B in the polymer chains are randomly oriented because that means there will be no definite orientation between A and B. For alternating copolymers, where the A and B are alternatingly positioned each other in the polymer chain, this is called the alternating copolymer. Block copolymers, so block copolymer is like that. We get one block of A, then another block of B, like present in the polymer chains. Then we can get block copolymers, graft copolymers, when there will be chance like that in our main polymer chain is another one monomer unit, but the side chain is another monomer unit, then we can get that graft copolymer. So how we can control that our polymer will be random, alternating block or graft copolymer, so that we can control by, so from the free radical polymerization we know that our growing chain have the radical, and this radical consume another monomer unit. Now this radical consume A or B, that depends on the rate constant of Kaa and Kab. Ka is the rate constant of the homo propagation, and Kbb rate constant of the cross propagation. So for that, if the cross propagation will be high, so then A going to consume B, and if the home propagation probability is high, the rate constant of home propagation is high, then A going to consume the A. So reactivity ratio of RA, that is the home propagation of rate constant of home propagation divided by rate constant of cross propagation, or the RB case is also the same, rate propagation of homo propagation of B and rate constant by divided by rate constant of cross propagation of BA. So now this, from this rate constant value we are going to get how we can get the random alternating block copolymers. Now let us consume that when the rate constant Ra is equal to 1, that is the probability of getting homopropagation and also cross propagation at the equal manner. So there will be no chance of getting, like we are getting, there will be various probability, we can get AAA, or sometimes we can get AB or AAB, like that. So there will be no orientation between the couple in the polymer chain. So they will be oriented randomly in the polymer chain. So then we are getting random copolymer. So for the random copolymer cases are Ra Rb equal to 1. So if the cross propagation is very high, that is at rather than the home propagation, that is the consumption of B is very high, when there will be a propagate change, so it will consume B. So then that type, so that the cases that the minimum of the homopropagation, maximum is the cross propagation, that is the 1 by infinity times, so it's almost equal to 0. So the random, so for the alternating cases our cross propagation is very high, so our Ra Rb almost 0 or equal to 0, then we can get, that is the alternating copolymers. So for getting the block copolymer, that is the, we need to, the homopropagation is the much faster, as compared to cross propagations. So reactivity of RAA is very greater than 1, then we can get the block. And for the gradient copolymers, so not like very much as compared to the block copolymers. It will be mm, between the random and block, that is we can get the gradient copolymers. So for getting random copolymers, our RA and RB equal to 1. For getting alternating copolymer, our RA and RB equal to 0. For getting block, so we should be, our homopropagation must be higher. Rate of homopropagation must be higher than the rate of cross propagation, that is the RA is very greater than 1. Then we talked about the liquid crystalline polymers. So liquid crystalline polymers are those polymers which can behave as a conventional polymers and also behave as a liquid crystals. So liquid crystalline polymers has the various applications in the high performance applications. So if we increase the temperature of the crystals, so what will go on? So it will be made, maybe go to the liquid. But if we capture, or if you get a such type of behaviors, that is why the both the liquid behavior and the crystal behavior we can exist, so then we can call as a liquid crystal polymers. So the to getting the liquid crystal polymers, so there will be two chains are present in the liquid crystal polymer generally. One is the flexible linkers, and as there is the rigid linker. The rigid linker like this we call mesogen, and flexible linker is like this. So these are going to the liquid crystal polymer like a crystal. So for the liquid crystal polymer there will be various type of phase like symmetric C phase, symmetric A phase, pneumatic phase, or isotropic phase. Also liquid crystal polymers as that behavior also different, like anisotropic behavior. So they have anisotropic means their physical properties and mechanical properties are the directionally dependent. Ordered molecular structures, so they have the rigid chain present in the polymer as is shown, the flexible and rigid chain mesogen type. So this mesogen have the ordered molecular structure, so they give the liquid crystalline behavior. High thermal stability, because this that mesogens have the normally the aromatic groups, so this aromatic group have the high thermal stability. Also this can high strength and stiffness, low coefficient of thermal expansion as compared to other conventional polymers, because this liquid crystalline polymer there will be two units are present. One unit may be that expansion will be high, but the rigid unit that expansion is not high with the increasing of temperature, so that can be give the dimensional stability of this liquid of this material. So the up to the because of this property, this material have the huge applications in the electronics, automotive industry, aerospace, and medical devices. So now we are going to solve some problem relation between that degree of polymerization and the average functionality. So for this, for a condensation polymerations, if there will be more than one functional group are present in the system, so we have to calculate the average functionality. So how the average functionality is the relation, you can get the relation between extent of reaction and average functionality. So if we're getting that, we have initially taken n0 number of molecules, and after reactions, so there will be presence in number of molecules. So the number of functional groups huge n0 minus n, and also we know that two functional groups are reacting, we are getting one molecules, that is that we need two functional group to get the one molecule. So total number of functional groups huge, that is the 2 into n0 minus n, because the two molecules going to give one functionality, that is the 2 into n0 minus n, and the number of functional group present initially in 0 by f average. So the extent of reaction equal to 2 into n0 minus n divided by n0 F average. Now we know that degree of polymerization is equal to n0 by n. So from here if we calculate that n0 by n, so what will be the 2 if we get, so this will be 2 by 2 minus p average, because we know that n0 by n equal to degree of polymerization. So we can relate that average functionality with the extent of reaction, and this extent of reaction is related to the degree of polymerization. So from this average functionality we can get the degree of polymerations if we know that how much the extent of reactions. So how we can calculate the average functionality for like a simple cases, if there will be 2 moles of glycerol and 3 moles of phthalic acid present in the system. So that is the summation of number of moles into its functionality divided by total number of moles present. So total number of functionality presents for these cases, so 2 into 2 moles of glycerol, and glycerol have 3 functional group, that is the 2 into 3. And for the phthalic acid there will be 2 functional group, that is we are taking 3 moles, so 3 into 2, so we are getting 2.4. The average functionality is F average 2.4. So from here we're going to solve another problem like that. For some application we have that nylon 6 is we need the molecular weight 20,000. For this we have add some monofunctional impurity, acetic acid. So what amount of monofunctional impurity we can add in the system that we can get that exactly 20,000 molecular weight. So in next class onwards I will tell about that how the monofunctional impurity are going to give our going to control our molecular weight. So from here we know the relation between the x and bar and average functionality. So if you calculate the degree of polymerization, so the degree of polymerization will be, you have to calculate the monomer unit, repeating unit molecular weight. So there will be 113, that is the xn bar equal to 20k divided by 113 is almost equal to 177. So now we have no relation between x and bar is equal to 2 into 2 minus p into F average. If extent of reaction is 100%, that is 1 into F average. So from here we are getting F average 1.987. So now we are giving as we are assuming that we are giving x moles of acetic acid in the system. So 1 mole of hexamethyldiamine and 1 mole of our adipic acids, which are function to like 2 2, and the function of this one is x, that is the total amine equivalent 2, total acetic equivalent is 2 plus x. Now the F average equal to 2 into equivalence of limiting group, or F average we can calculate like this: 2 into functionality of this one, so 1 into 2 plus 1 into 2, that is the 4, divided by total moles we are giving 1 plus 1 plus x, that is the 2 plus x. So from where we are calculate the value of x. So from here we can told that if we add this much amount of x into our polymerization systems, we can get the exact molecular of 20,000. So thank you to join.